have to understand the business problem. Okay, what is the business problem here? Classification of MNIST dataset, MNIST handwritten digits using the artificial neural network. That is our case study. Now, first of all, you have to understand the problem. That means here our problem is we are giving the input as a handwritten digit, it is a 5 or 6 or what it may be. We have printed the corresponding class label. That is our problem statement. And in order to perform this one, we require some library files are required. Okay, and then you have to read the dataset. Read the dataset means here the dataset is maybe a MNIST dataset, and then data splitting into training part and testing part. That means the MNIST dataset contains 70,000 handwritten digits are there. 70,000 handwritten digits are there. Out of 70,000 handwritten digits, okay, that means here it contains 784 features are there. Totally, we are having the 70,000 handwritten digits are there, and it contains 784 features are there. Corresponding class labels are there. Class labels, okay, y cap is there or y is there. Okay, y, and out of 70,000 images, okay, we are dividing. We are giving the for model. We are giving the for model 1 to 60,000 images for the training purpose, and the remaining 10,000 given for the testing purpose. Okay, now so this is called as a x underscore training value and y underscore train value, and this is called as a x underscore test value, and this is called as a y underscore test value. So like that, the 70,000 images are converted into training part and testing part. Okay, now so now each training part contains corresponding features are there, and corresponding class labels are there, and testing also contains x testing features are there, and y test values are there. That is called as a splitting the data into training and testing. Then you have to perform the data pre-processing. What is the meaning of data pre-processing? If any missing values are there, then at the time you have to replace with the missing value to maximum value or minimum value or average value, or converting the 255 value 0 to 255 value into between the 0 to 1 values. Okay, this is one type of thing is called as a data pre-processing. And then before converting the after performing the pre-processing, then we are going to convert the next step is called as a flattening. What do you mean of flattening? Flattening is nothing but converting all the 28 by 28 pixel values into single vector. Okay, into single vector is called as a flattening. All the 784 features into single vector is called as a data flattening. Then build the model. Building the model. So that means building the model nothing but here based on your input features, based on we know the corresponding class labels. This is the output value, y cap value, and this is your input value, input features. And here we are going to define the how many hidden layers are there and how many neurons are there in the corresponding hidden layers. Like that, we are going to define the things is called as a model building. Model building. Then model compilation. After model compilation, model building, we have to train the model itself of compilation. Okay, now that means if any loss is there, we are going to update your weight values with respect to our optimizers and the loss functions. Okay, we'll see with the code. And then model training, and then model evaluation, and then model prediction. These are the different steps you have to follow in order to develop your model. Okay, now so now we are going to see our code in the Colab. Okay, now what are different steps are there? Understand the business problem, import the library files, read the data set, and data splitting into training part and testing part, data pre-processing, data flattening, model building, model compilation, model training, model evaluation, and model prediction. They are the 10 or 11 steps you have to follow in order to develop any artificial neural networks program. Okay, now we will see the code for our model. Okay, now so already we discussed the things. Now so the steps are, so normally the Colab, the Colab. Colab is a repository, is freely available resources to run your program. Automatically, it contains the Python environment and everything. Okay, this is a platform to run your machine learning programming or deep learning programming and everything. Okay, now here, first of all, you know the steps. What are the steps? What are the steps are there? Understand the business problem, import the required library files, read the data set, data splitting into training part and testing part, data pre-processing, data flattening, model building, model compilation, model training, model evaluation, model prediction. They are the 11 steps you have to follow. You have to execute in a model. Okay, now then first step is a business problem. The business problem is here. You have to give read the data set of the MNIST data set and classify the given image is a whether it is a 9 or 1 or 2 like that. Okay, classification of MNIST data set. That is a problem statement. And then in order to run this program, first of all you require the some hidden library files. So here the library files are TensorFlow, import TensorFlow as a TF from TensorFlow, import Keras from Keras.models, our sequential model. What is the meaning of sequential model? We are performing the steps from the input layer to output layer in a sequential manner. That's why it's called as a sequential model. Okay, that is available in the Keras.models import sequential model. Now, Keras data from Keras data layers data import to dense layer drop out to activation function. That means our model is a fully connected layer. Fully connected layer. That's why it's called as a dense layer. Okay, na? And sometimes we are going to drop out the some neurons in our model layers. That's why we require the drop out. And also it contains some activation functions. Okay, na? What are different activation functions are there? Like sigmoid, tanh, relu, softmax. So we are going to use all the activation functions in our model. That's why we are going to use the activation functions. Sometimes we are going to use the optimizers in order to minimize the loss function. That's why you require the Keras dot optimizers and import stochastic gradient descent algorithm is there. It is one type of optimizer is there. So with that we are going to minimize the loss functions, and then some this is the there is some library files are required to your to run your model, and then read the data set and split the data set into training and testing part. So here MNIST data set is already available in our Keras data set. That means defaultly the data set MNIST data set is available in Keras. So from the directly Keras data set, we are importing the data into load the data set and divide the data set into two parts. What are two parts? What are two parts now? X train and Y train. Sorry, training part and testing part. Each part contains two things once again. But that is called as a X train and Y train, X test and Y test. A training nothing but all the 784 features of the 60,000 features, 60,000 images. Y train nothing but Y underscore train nothing but corresponding class labels of the 60,000 images. Okay, na? X underscore test nothing but all the 10 remaining 10,000 images of the test data features, and Y underscore test nothing but corresponding actual class labels of the testing data. Okay, 10,000 test data class labels. Okay, now. So now from that we are going to display one image. For example, plot data mat show or matrix show. Okay, x underscore train underscore x underscore train of 0. Okay, now that means here the first row data. If you display that one, what happened now? This is the corresponding value. So what the value now? This is an image of the 5. Okay, now handwritten digit 5. Now x underscore train underscore 0. Okay, now this is the image representation. This is the corresponding value. Okay, now this is the 5 value. Now corresponding the what is the value? Y underscore y underscore test and train underscore 0. That means it gives the output as a y value. Okay, now what is the y value here? Corresponding class label is 5. Okay, now so this is the input value and corresponding class label is 5. Okay, now this is the representation of the what we call x underscore train value. So it contains all the 60,000 images. So this is a one image. This is the one image. Okay, this is one image. That image contains 28 rows and 28 columns. Like that, how many images are there? Totally 60,000 images are there. And the corresponding to this one, x underscore train underscore train dot shape. 60,000 images are there, and the size of the image contains 28 rows and 28 columns. Corresponding y underscore train equal to 5 comma. Okay, that means all the 60,000 class labels of the corresponding things. Okay, now. Now, y underscore train dot shape, that gives 60,000 class labels are there. Okay, now. Now, x underscore test of 0 equal to, here 28 rows and 28 columns are there. The corresponding label equal to 7. Okay, now. So matplot show dot mat show x underscore test of 0 equal to corresponding class label is so here this is the testing data. In the testing data, the first element is equal to 7, and the corresponding class image is 7 only, and we are going to get the output as a 7 only. Okay, now. So here x underscore test equal to, it contains 10,000 images are there. Each image size contains 28 rows and 28 columns. Okay, now. 28 rows and 28 columns. Now y underscore test of 0. What the corresponding class label? 7. So what the corresponding image now? 7 only. So that means both the input image and corresponding features are correctly classified. Okay, now. Now x underscore test of shape equal to 10,000. 10,000 images are there, and each image contains 28 rows and 28 columns are there. And y underscore test of equal to y source. It shows all the corresponding class labels of the 10,000 images. Okay, now y underscore test dot shape. That means it contains 10,000 class labels are there. 10,000 class labels are there. So like that, that means the data is divided into two parts. One is the training part and the testing part, and each part contains corresponding features and corresponding class labels are there. So that means that is called as a data splitting. Then the fifth step is called as a data pre-processing. What meaning of data pre-processing here? That the pixel values are converted into divided by the what are the values are that divided by the 255. The what the maximum value? Maximum value is equal to 255 now. So the training part and the corresponding testing part is divided with 255 value. After that, what happened? They're going to get the values between the 0 to 1 only. 0 to 1 only. That is the one type of data pre-processing is applied on the our given data. And both X-train data and Y-train data are performing the data pre-processing. And after that, what happened? We are converting that into data flattening. What do you mean of data flattening? The data flattening is nothing but the input values are converted into single vector value. So both the training part and the testing part are converted into flattening. Okay, now with the help of reshape, x underscore train dot reshape length of the our input image equal to x underscore train, that is converted into 28 by 28. So that image is converted into a single vector. This is called as a data flattening. Both training part and testing features are converted into single vector. Okay. After flattening, what happened? 60,000 images are there, and each image converted into 784 features. So previously, it is a 28 by 28. 28 by 28. But what happened here after applying the data flattening, it converts into 784 features. Okay, now. So now how many images are there? Totally 60,000 images are there, and here you are applying the convert that into single vector of 784 features. Okay, now we are going to build the model. What the model here? Our model is here. Sequential model, and then we are applying the two layers are there. Two layers. Okay, what are first layer? We are going to add the first hidden layer. This is one model, hidden layer 1. Okay, this is called your hidden layer 1. Okay, in the hidden layer 1, what happened? How many inputs are there? So for example here, So here 784 features are there. Okay, that means all are having the input features 0. These are the input features. Okay, and we are having the output features are there. Output features are there. In between we are creating the one hidden layer one, and we are going to create one more hidden layer. Okay, so 1 to 784 features. Now what happened here? The first layer, this is your hidden layer one. Okay, in the hidden layer one, we are going to have the 784 neurons are there. 784 neurons are there. This is the hidden layer one. Okay, in this hidden layer one, we are having the 784 neurons are there. We can create a number of neurons. Okay, and here each and every neuron is going to be connected with each and every input layer. Okay, this is called as a fully connected network. This is called as a fully connected network. Okay, now so see this one in the model dot add dense layer network fully connected layer. In the fully connected layer, how many inputs are there? How many neurons are there? 784 neurons are there. That means in the hidden layer one, we are having the 784 neurons are there. For these 784 neurons, what is the input here? What is the input here? From the input shape. What is the input shape? That is 784 features are there now. From the 784 features, we are going to get the input. Okay, from this input, we are going to get the input. Okay, now, and then here we are going to perform the activation function. What is the which activation function applying here? ReLU. Okay, now that means in this hidden layer, we are going to perform the sigmoid activation function, then perform the ReLU as a activation function. Like that, for each and every neuron, here perform the sigmoid and then apply the ReLU activation function. Sigmoid and ReLU as a activation function, the hidden layer one. Okay, now, and then we are going to create one more hidden layer. What is the hidden layer now? Okay, in the hidden layer 2, in the hidden layer 2, how many neurons are there? 10 neurons are there. That means in the output and the hidden layer 2, we are having the one more. How many neurons are there here? 10 neurons are there. Only we are having the 10 neurons. Okay, now we are having 10 neurons. We are having the 10 neurons are there. Okay, 10 neurons, and each neuron also performing the activation function. Sigmoid activation function is a fully connected layer. Okay, and fully connected layer. Okay, and in the hidden layer 2, we are having 10 neurons, and each neuron perform the sigmoid activation function, sigma summation, and then perform the activation function ReLU. Okay, now that is the third step. And then after that, we are having the output layer. This is your model. Okay, in the output layer, how many neurons are there? 10 neurons are there, and the activation function is a softmax as a activation function. Now here in the output layer, we are having the 10 neurons are there. We are having the 10 neurons are there. Okay, 10 neurons are there, and each neuron also apply the summation and activation function. Now here activation function as a in the output layer, we are using the activation function as a softmax. Why are you using the softmax as activation function? Because of we are using the multi-class classification prediction of our input image. Okay, we are giving the suppose 5 as input image, that is converted into flattening. That flattening is given to input layer to the model. Now it is a multi-class classification problem. That's why in the output layer, we are going to use the activation function as a softmax activation function. So here in the output layer, we are going to get the probability of the each and everything. Suppose this is a 0.01, 0.2, okay, 0.2, 0.03, or sometimes 0.9, okay, 0.4, like that. Okay. Now there are all the 10 values are we going to get. Among all the 10 values, which is having the highest value, then that becomes your class label. So like that, we are going to develop the model. Okay, this is called model building. Now these are the steps you have to apply in your model building. So the first step is called as model equal to sequential model, and we are creating a header layer 1, and we are creating a header layer 2. Header layer 2. That means in between the input layer and output layer, we are having the only two header layers are there. In the first header layer, we are having the 784 features are there, neurons are there. In the second header layer, we are having the 10 neurons are there. In the output layer, we are having the 10 neurons are there. Okay, now. So like that, we are going to build the model, and then uh, model summary. Model dot summary. It use the sequential model. So here, see this one here. In the first layer, in the first header layer, we are having the 784 neurons are there, and the second header layer we are having the 10 neurons are there, and we are having the output layer we are having the 10 neurons are there. Uh, Totally here having the 6 lakhs 15,404 neurons are there. That means 784 neurons are connected to 784 neurons input features, and then each neuron connected with the bias value. That's why we are getting the all the 6 lakhs 15,440 neurons parameters are going to perform in the header layer 1. In the second header layer, okay, we are performing the 7,815 operations are performed in the second header layer. Okay, that means 784 neurons are connected to 710 neurons. That means plus each neuron um, contains added to bias value. So that means we are getting the 7,850 neurons. In the output layer connected to 100 110 operations you are going to perform in the output layer. So like that you are performing the model. Okay, now model dot summary. After that, what happened? We are going to draw the our model architecture with the help of model dot plot. Okay, from the TensorFlow dot keras dot utils import to plot underscore model. If you draw the plot image of the our model, plot underscore model dot model comma to the file to underscore file equal to model dot png and show underscore shapes dot shapes equal to true, um, show underscore layer underscore names equal to true. If you execute this statement, automatically whatever the developed model, that model represented in the form of a one graphical representation. Okay, now then after that we have to compile the model. Okay, in order to compile the model, what happened? Model dot compile. We have to use the two things. One is a loss function, and we are using the loss function, and we are using one more thing is called as a optimizer. Here we are using the optimizer as a ADAM, and loss function as a sparse categorical cross entropy. Okay, in order to minimize the loss function, we are going to use the categorical cross entropy as a activation function. Okay, in the output in the compilation model. Okay, now and accuracy as a matrix like accuracy, we are going to predict the output in the form of a accuracy. Okay, now then after that you have to train the model dot fit with the fit function is used to train the model dot fit. For this we have to provide the our training data. Okay, in the form of x underscore train underscore flattening data and corresponding y underscore train data. That means features you are provide all the 784 features of the 60,000 images and the corresponding class labels you have provide, and you have train the model in 5 iterations. F(x) equal to 5 iterations. See this diagram, see these steps here. Initially the accuracy is very low, but the loss is very high. Okay, now after iterations are over, after number of iterations are over, what happens? The accuracy is going to be very high, the loss is going to be decreases. So like that we have to perform the different types of epochs. Okay, now so if you increase the more number of epochs, automatically the initial the accuracy is going to be increases. And then we have to evaluate our model dot to evaluate x underscore test underscore flattening and y underscore test. With the help of testing data, we are going to predict our model accuracy. Okay, so now here with the help of our test data, what happened now? We are getting the output accuracy as a 0.972. Okay, and loss equal to 0.1. Okay, that means the accuracy, the predicted value is going to be get the correctly classified. Okay, now then model prediction. Suppose you are predict the new value, y underscore predict equal to model dot predicted predict for this we are providing the new data. So x underscore test underscore flattening, that it contains our test data. Based on the test data, we are going to predict the corresponding output values, corresponding class labels, and then these are the outputs are there. These are the corresponding predictive values. Here, see this one. So among all the things values, which is having the highest value, that becomes your corresponding class label. So for example, here y underscore predict of these are the 10,000 corresponding predictive values. So we are checking the first value. We are checking the first value. So y underscore predictor of 0 equal to, that is first test data value equal to, it contains 10 different values are there, 10 different values. Our class label, our property statement contains 10 different class labels are there. Okay, na? So 0, 1, 2, 3 like that. 0 to 10 class labels are there, na? 9 class labels. So here among all these things now, so which is having the highest value here? 1.2 like that, 1.13, 4.6, 7.7, and 5.12 or 1.0 like that we are having the. So at the index 7 value, that it contains 9.9, which is having the highest value, So the corresponding class label is 7. Why? Among all the 10 values, 10 index values, okay, the first index value is 0, and second one 2, 3, 4, 5, 6, 7, and 8, 9. Among all the index values, the 7th index value is having the highest value. So that's why we are going to assign the class label as a 7 for the given input data. Okay, now. So now if you draw the graph for the first input value or test data, plot dot mat show x underscore test of 0, Okay, the corresponding image is 7 only. Okay, what we are predicting the corresponding class label here? 7 only. See 0, 1, 2, 3, 4, 5, 6, 7. So that means our predictor value and input value both are the same only. Okay, now. So y underscore predictor equal to 0. Okay, so that is 7. So corresponding np dot argmax of y underscore predictor of 0. Okay, that we are converting into values in the form of values. So we are getting the value as a 7. So that means our input value is 7 only, on predict values also 7 only. Like that, we are going to develop your model now to predict your class label for the with help of artificial neural networks. So this is about case study how to predict the class label for the given image with the help of artificial neural networks. So here we have to perform the different steps are there. What are the steps now? What are the steps you are perform? The steps are, okay,